Assalamualaikum warahmatullahi wabarakatuh, and a very good day. So we meet again for I think the second part for the topic 3, which is the power transmission, power generation transmission. Okay, so we continue for the transmission line. So for your recap, so the transmission line can be divided under two categories, which is the overhead transmission line and what I call the other one is the underground transmission line. Okay, and for the overhead transmission line, usually the cables are bare. There is no insulations, and uh, this is the reason is actually is so that the heat can be dissipated easily uh, through the environment and so on. Okay, and in this part, we will actually try to model the transmission line, okay, with an equivalent electrical circuit which has a resistance. We can model the transmission line as a resistance, and then inductance and also the capacitance. Okay, so as you can see in this slide, so usually the resistance and inductance are a series parameters, while the capacitance, which actually represent the electrical field, actually is between the transmission line, phase A, phase B, okay, is actually a shunt parameters in the circuit. And in physically, all line parameters are distributed uniformly along the line. However, to simplify the line analysis, typically the parameters are assumed as lump elements at a given point in the equivalent circuit. Okay, so in this section, we will describe the model techniques available to lump the line parameters based on the length of the lines, which can be divided into three representations. Okay, so we have short line representation modeling, medium line representation, and the last one, which is a long line representation. But however, for this course, we only will cover the first two, which is the short line and the medium line, while the long line representation will be covered in the your electromagnetic theory course. Okay. So this is the short line representation. As you can see, it's a very simple, okay, a very simple model. So this short line representation is only applicable with the transmission line that is less than 80 kilometers. Okay, and as you can see here, the parameters or the components that exist is only a series component, which is the resistor and the inductance. Okay, while the capacitance effect is actually insignificant. So as you can see, there is no capacitor here. So this is actually the perfect circuit for the short line representation. Okay, always for this analysis, we always consider a single phase, even though you have a three phase. But since we assume that the other phase is balanced, so we only consider per phase circuit for our analysis. And should be noted here, the VS and VR, also IS and IR is actually phase value. Okay, they are all phase value. So because we are concentrating on the per phase equivalent circuit, so the value of VS, VR, IS, and IR should be in phase value. So as you can see here, VS and IS is the phase voltage and phase current at the sending end of the line, while VR and IR is the phase voltage and current at the receiving end. R is the total resistance per phase, while XL is the total inductance, which is a reactance actually, per phase in ohm. And the line impedance per phase, which is the Z, you can actually write as a very simple one, which is R plus JXL on in polar form is Z with an angle of theta Z. So normally, as you can see from this circuit, IS and IR is actually the same because this is a single loop. So meaning that IS and IR is the same. Okay, so IS and IR are the same, while voltage VS and VR are different due to the voltage drop across the impedance. Okay, so we can write down like this based on the KVL, which is VS is equal to the voltage received end plus the voltage drop inside the impedance, while the current, which is IS, is equal to IR. And normally for our analysis, VR is taken as a reference phasor. Okay, so the angle of the receiving end of the voltage is 0. So in the matrix form, you can write down as this one. Okay, so the sending end, and then the matrix, the A, B, C, D parameters here, and this is the receiving end. Okay, so from here you can see A is A is 1, B is equal to Z, C is equal to 0, and D is equal to 1. And to check whether the matrix is correct or not, you can always actually do this calculation, which is A multiplied with D minus B multiplied with C. It must be equal to 1. Okay, so if the answer is equal to 1, meaning that your matrix is correct. So example, a 30 kilometer, 3-phase 50 Hertz transmission line is transferring power to a 500 kilowatt load with power factor of 0.9 lagging. The load voltage is 10 kilovolt. Given resistance and inductance of the line per phase of 0.1 ohm per kilometer and 0.4 to 4 millihenry per kilometer, let's calculate the current and the voltage at the sending end of the line. Okay, so what you need to do first is actually to get the R total. The R total is actually 0.1 multiplied with 3 kilometers. So this one you should get around 3 ohms. Okay, and then you need also to get the X total, the reactance total, which is this one is actually omega L multiplied with the kilometers length. So this one should be 2 pi multiplied with 50 hertz multiplied with 0.424 multiplied with 30 kilometers. Okay, so you will have your Z total is equal to R total plus GXL total. Okay, and this VR, this one is actually V line. Okay, so always remember that when you refer to a power system, so usually the voltage here is referring as a V line. So to get, because we are actually analyzing per phase equivalent circuit, okay, so we need to actually convert this line voltage into its line value. So 10 kilovolts, okay, over square root 3. So, okay. And you have this solution, okay, the phase voltage and current at the load terminal. So you always use that VR is our reference phase. So that's why we have a 0 angle here. So your VR here. And from VR, you can, and then it's also given the power, which is a 500 kilowatt with the power factor of 0.9 lagging. Okay, so from that, okay, you can always calculate IR. So IR is 32.1. This is the value. So from the inverse cos of 0.9, you will receive 225.8 ohm, 0.8 degrees. But this one didn't mention whether it is positive or negative. So, but by referring to this information from the question, it is a lagging, meaning that the current is lagging the voltage. Okay, so the voltage is 0, meaning that the current should be lagging the voltage by negative 25.8 degrees. Okay, and as mentioned before, this is your Z total, which is 3 plus J4. Okay, you will have this value. And then the answer is for the IS. Okay, so we know that IR is equivalent to IS. So just use IR value, which is 32.1 with an angle of negative 25.8 degrees. And to find the phase voltage at the sending end, so you can always use this formula. Okay, and then you will receive the answer here. And this is actually V phase. So to get the value of V line, you need to multiply with the square root 3 with an angle of 30 degrees. Because we know that the V phase, the relationship between V line and V phase is square root 3 V phase with an angle of 30 degrees. Okay, so and then we have also self-assessment questions. You can maybe we will discuss this during the class. So thank you very much. We will continue on the medium line representation.